Alright gang, here we go. So this is Chem 1, Unit 6. Part 1, we're talking about measurements. We're going to talk about scientific notation. Should be a lot of fun. Alright, so let's get started. Here we go. So in chemistry, a lot of what we have to do is we're going to be, doing experiments and making observations. And so far, primarily the type of observations you've made thus far in chemistry are qualitative observations. Okay, so qualitative is where you're keeping track of the qualities, all right? So these are like the description words, like their color, shape, texture, stuff like that. So those are qualitative observations, okay? An important part of chemistry is the quantitative part. And so starting now and pretty much through the rest of the semester, we're going to be focusing on quantitative observations. All right, so this whole unit is about how to make accurate quantitative observations, how to keep track of the math involved with quantitative observations, and so on and so forth. So it's just the quantitative ones are the observations that refer to the number, and they always involve some sort of measurements. Okay, so like height, weight, density, volume, temperature. There's lots of different options. All right. So measurements always have to have units, okay? And you're probably used to this in your other science and math classes, keeping track of your units that are involved, okay? All measurements come from instruments. All right, so instruments, so these instruments, this is just not like a piano or a trombone or anything like that. This is like a fancy way of saying whatever object you're using to make your measurement, okay? And since we're using different instruments, and these instruments are made by humans, and humans have inherent inaccuracies, whatever thing you're using is always going to have a certain measurement of its inaccuracy, okay? And so that inaccuracy is dependent upon how well that thing was made. Okay, and so when we're recording our measurements that we're making, we always have to keep track of this very important idea here, all right, and it's underlined. It says, when recording measurements, we record all the known digits plus one estimated digit, okay, all known digits plus one estimated. Okay, so let's practice this real quick. So if we, so these are just rulers, and you learned in like second grade how to measure things from a ruler. So this should be easy to get an idea of what's going on. So we've got this piece of, I don't know, granite or something, and we need to get the length of it. Okay, and let's just assume these are. Let's assume these are centimeters here. All right, so we have 0, 0.5, 1.0. So if we look at each of these lines, 1, 2, 3, 4, 5. So each of these lines is a tenth marking, right? So this is 0.1, this is 0.2, this is 0.3, this is 0.4, right? So on and so forth, 0.6, 7, 8, 9, and then we get to 1, and then 1.1, right? 1.1. Anyway, so when you're making a measurement, what you have to do is you have to think, okay, what do I know for sure? Well, I know for sure that this piece of granite is between 1.3 and 1.4. Right, it's somewhere in between those two values. So that's the known part. Remember, it has to have all the known digits, okay? So we know for sure that this guy here is 1.3, okay? Right? And then we have to do one estimated digit. Okay, so we have to make an estimation about where this guy is between 1.3 and 1.4. Well, it's not quite half, because like my guess is that half would be somewhere in there. So maybe it would be like 1.36, okay? So that 6 is my estimated digit right there. Now you might be tempted to be like, oh, it's 1.365. That's no good. We can't say 5 because that would be two estimated digits, because 1.3 is what we know for sure. It's definitely bigger than 1.3, but it's not quite 1.4. Okay, so that's what we mean. So this guy would be 1.36 centimeters if we assume each of these guys are centimeters here. All right, let's do one more. Okay, so here though, we've got a ruler and it's marking centimeters. We know that for sure because it says centimeters. We're measuring the length of this dashed line. Okay, and so notice how in here we don't have any estimate, we don't have any lines delineating what's the length between 0 and 1, 1 to 2, 2 to 3. All we know for sure is that our line here is at 5, and to me it looks like it's just past 5 somewhere, right? So okay, so we know for sure that we're at 5. Okay, that's all we know for sure. That's all that this gives us. That's all our lines tell us. So then we have one more estimated digit. Well, So really, our only option is that we can say, well, it's either at 1 or it's at 0. And so really, this is our estimated digit here. So, and you could say 0, and like arguably, you could say that that's pretty good guess as well. Because it's such a shade past 5 in my opinion, and if you make the measurement, you might make a different call. So anyway, so that's how we make measurements in chemistry. It's all depending upon the instrument. We'll do a couple practices in class to help you get an idea of how that works in real life. All right, SI units. SI stands for Système d'International or something like that. It's French. Okay, it really stands for International System of Units. So this is the system of units all scientists have decided upon using, and so that we're all using the same units. So very important that we're all using the same units. All right. And it's based off the metric system. And you've probably learned about the metric system a lot in different classes. In the United States, we don't really use the metric system just because that's not what people are used to using. But in my opinion, it's by far better and easier to use. But anyway, and so the metric system is based off multiples of 10. All right, so, and that's really what makes it easier, is because we can just keep track of, oh, that's always 10 times bigger, 100 times bigger, 1,000 times bigger, so on and so forth. All right, so here's some examples of different SI units and what they use to measure. So if we're measuring length, we use meters. If we're measuring mass, we use kilograms. Times in seconds. Temperature is in Kelvin. Amount is in moles. If we have current, it's in amps. And luminosity is in candelas. Okay, so really we don't really care about amps or candelas, but we will be measuring things here. Oops, these guys here in chemistry. This is really what we'll focus on. And meters, even then, we won't really talk about meters very often. So really it's just kilograms, seconds, kelvins, and moles are the most important from those lists. The other nice thing about SI units is that they can be combined to help us get other units. Okay, so these are other SI units, but these are combined units. So area is in meters squared, volume is in meters cubed. I mean, that makes sense, right? Because area is length times width, and volume is length times width times height. Okay, and so we get the meters squared, meters cubed. And density, we'll talk about that at the end of this unit. It's in kilograms per meters per second. Molar mass. Okay, the SI unit is in kilograms per mole, but really most often we use grams per mole for our molar mass. Anyway, all right, and we'll kind of talk about those more. You don't really have to have those memorized. These over here you should probably memorize, but these here, okay. All right, now SI units and prefixes. Now the nice thing about the metric system is that in order to help us keep track of how many 10 factors we've used, or we're going to use these prefixes to help us keep track of what's going on. And here's a giant list of all the prefixes that we could possibly use. So okay, so here we can really take these prefixes and we can add them in front of any unit. Okay, so these C's, so the lowercase c here tells us that we're talking about centi over here. See the centi? Okay, so this is saying centimeter. And then centigram, centiliter, centikelvin. All right, and so really that means is that we're talking about a unit that's 10 to the minus second of whatever unit we're talking about. All right. So here's the ones that I would like you to have memorized. Okay, so mega, kilo, deci, centi, milli, micro, nano, pico. Okay, mega is abbreviated with a capital M, and it is 10 to the 6th power. Okay, kilo is with a lowercase k, and it's 10 to the 3rd. So really what this is saying is that for every one of our base unit, okay, we have 1,000 kilos, or there's 1,000 of our base units in 1 kilo. Okay, deci is with the lowercase d, okay, and it's 10 to the minus 1. Okay, so here we've kind of gone from, so if this is our base, we've kind of gone from having something that's lower or bigger than our base unit to something smaller than our base unit. Okay, centi, all right, so this would be like the centimeter, is a lowercase c, and it's 10 to the minus second. So there's 100 centis in one base unit. And then milli is a lowercase m, and it's 10 to the minus third. Okay, micro is my personal favorite because it's this cool little U. So it looks like a U, right? There's the U part of it, but it's got like a tail hanging off the front. All right, and that's 10 to the minus 6th. Nano is a lowercase n, and it's 10 to the minus 9th. And then pico is with the lowercase p, and it's 10 to the minus 12th. Okay. All right, so just to give you a little better idea, a little better idea of what's going on. Let's see, I can go, nope, nope, nope. Ah. So let's draw ourselves like a little metric line here. So we'll call this the metric line. All right, so if we draw ourselves a line, okay, and we say, all right, here's our base unit. All right, here's our base unit. So this could be whatever SI unit we're talking about, meters or grams, Kelvin, okay, doesn't matter. All right, so there's our base unit, okay. All right, so remember we had mega, so on the left side we'll put things that are bigger than our base unit. So we have mega, and remember mega was a capital M, and it was 10 to the 6th. And then we have kilo, right, kilo here is with a lowercase k, and it was 10 to the 3rd. All right, and then on the other side we had a whole slew of smaller ones, right? So we had deci, okay, so deci was a lowercase d, and it was 10 to the -1st. And then we had centi, all right, and it was a lowercase c, and it was 10 to the -2nd, all right. And then we had milli, and it was a lowercase m, 10 to the -3rd. Then my favorite, micro, all right, micro was a lowercase u with the tail on the front, okay, and that was 10 to the -6th. And then we had nano, N-A-N-O, lowercase n, and that was 10 to the -9th. And then finally we have pico, which is a lowercase p, and that was 10 to the -12, all right? So there's our metric line, all right? So really what this is saying is that things over here are smaller than our base unit, things over here are bigger than our base unit. So if we have a millimeter, that means we have 1,000 millimeters in 1 full meter, okay? Or, and here in a couple of units, or parts here, we're going to use this number line to help us convert between one and the other. So make sure you keep track of this in your back of your mind, because when we get to dimensional analysis, this will become very, very important. All right. Now, scientific notation, all right. Scientific notation help us simplify our measurements, because things in chemistry are either really large numbers of things or a really small measurement. All right, when we react, like even a gram, which is a very small amount of a chemical, there's millions and millions of atoms in that gram. Okay, and so instead of writing out a number that's got like 5, 6, 8 zeros before or after it, we're going to use scientific notation. Now, you probably learned scientific notation in middle school, hopefully. Okay, so hopefully this will be a little bit of a review over what's going on. All right, but we're going to use scientific notation almost exclusively. All right, so scientific notation helps us simplify these measurements. We don't have a bunch of zeros going on. All right, so the way scientific notation works is it's a product of two numbers. You've got your n. This is known as the coefficient. Okay, the n is the coefficient, and it's being multiplied by 10 times some number. Okay, and this number up here always has to be a whole number. Okay. Now, n always has to be some number between 1 and 10. So it's always going to be 1 point, or it's going to be, it can't ever be bigger than 10, okay, and it can't ever be smaller than 1. So essentially what we're saying is your n always has to have some number and then a decimal and then the rest of the numbers. Okay, so that's essentially what we're saying is one digit to the left of the decimal and then the rest to the right of the decimal. That's what that means. Okay, m is the exponent, and it's always going to be a whole number. Okay, and and it can be positive or negative. If the exponent is positive, that means the number is very big. All right, it's a large number, and we've moved the decimal to the right. So here we've got 2.35 times 10 to the 5th. Notice that it's a positive 5 here. This is a positive 5. So that means we're going to move the decimal to the right. So we're going to go 1, 2, 3, 4, 5. And we write in zeros for the rest of these guys. So we get 235 with 3 zeros afterwards. So we get 235,000. So that's what these two numbers mean. These are the exact same number. Okay, if the exponent is negative, that means your number is very small, and you're going to move your decimal to the left. Okay, so we're going to take our decimal. That's right here. We go 1, 2, 3, 4, 5. We add our decimal because that's where we moved it to. All right, and we write in zeros for the. Oh, why did you go away? All right, here's our decimal. 1, 2, 3, 4. Okay, and so we get our 4 zeros. It's kind of There, my zeros got funky on me, didn't they? So anyway, 1, 2, 3, 4 zeros, and then 10 to the minus fifth, so that we get this number here. So there's this guy here. All right. Let's do some practice. So we're going to rewrite the following measurements in scientific notation. So we're going to take our decimal, and essentially what we're going to do is just move our decimal so it goes over. So 1, 2, 3, 4, 5, 6. So this becomes 1.2 times 10 to the 6th milliseconds. Pretty easy, right? Our decimal's right here. So we go 1, 2, 3. So this becomes 5.946 times 10 to the 3rd feet. Notice that here, I didn't bother writing in all these zeros because these zeros are simply placeholder zeros, right? They don't mean anything. They were just extra zeros. The whole point of writing in scientific notation is I can get rid of those placeholder zeros. But here, this 946, these are not placeholders. These are important numbers. These were measured, okay? So I have to keep those written in, all right? Now we're going to do the same thing with our seconds here. We're going to take our decimal. We're going to move it until we get one number to the left. So this becomes 3.005639. So 1, 2, 3, 4 times 10 to the 4th seconds. Notice how I'm making sure I write in my units. That's important. It tells me what the heck I measured. All right, and one more. Now, oh, this one's different. We're moving it to the right instead. 1, 2, 3, 4. Now, this number's smaller than 0. Remember, smaller numbers are going to have negative exponents. So this becomes 3.45909 times 10 to the minus, wait, how many did I have? 1, 2, 3, 4, minus 4th atoms. Now, see, I got distracted by this unit here. This is saying that we've got, like, 3/10,000ths of an atom. What does that even mean? This is a stupid unit. Who came up with this example? This is garbage. Anyway, so that's why I got distracted. Anyway, it's kind of silly. All right. So scientific notation, some more. So now we're going to take our number written in scientific notation and convert it back into a regular number that we're used to using. So we're going to take our value. Remember, if it's a positive, that means we move it to the right. Now, you have to keep track of what it's asking, because here, you have to think about, okay, the positive means bigger than 1, all right? That's really what it means. So we're moving our decimal to the right because we know our 2 has to be bigger than 1. So this becomes 2 with 3 zeros after it, so it'd be 1, 2, 3, right? You could also do it just by moving the decimal to 3 and write in your 3 zeros. So 2,000 yards, all right? Garbage unit. This is not metric, garbage. It's garbage. Anyway, all right, now we're in hours, so now this times 10 to the 6th. We're going to move our decimal place over 6 times. So we got 1, 2, 3, and then 4, 5, 6. We add 3 zeros, so it becomes 1,405,000. And if we're really fancy, we could add in commas. And so this be 1,405,000 hours. All right, and then times 10 to the minus 4th. So we're going to move our decimal 4 to the left because it's negative. So we go 1, 2, 3, 4, 1, 2, 3, and our decimal goes here. So it becomes 0.0001503 liters. Nailed it. All right, and then another minus fifth, so we go 1, and you can see here that we're just going to have 4 zeros and then 2, 3 pounds. All right, so pretty easy here, right? Converting back and forth. It does take a little practice. Biggest problem I see students messing up with is this idea of, well, like here, I moved my decimal to the left, but it's positive. But that's because you have to keep track of which way you're going. Are you converting it to or from scientific notation? So make sure you do some practice so you don't screw that up. Now, last thing, and this is really, really important that you understand how this works. Okay, now, because we'll be doing lots of math with these numbers that have exponents, or that are written in scientific notation and have these exponents. And I see that students screw this up all the time, okay, even in physics and Chem 2. So make sure you pay attention. Now, this is the way I suggest to put it in your calculator. This is using a TI. If you have some funky Casio or something like that, come and see me and we can figure out how to do it on your calculator. Okay, on all of these TI calculators, they have these values here that they have you have your second, and then above this comma button is this EE right here, okay? This is your exponent button. This is used to write scientific notation. So let's say if you had this guy here, if you were taking 1.7 times 10 to the 6th, and you were dividing it by 2.7 times 10 to the minus 11th. All right, this is how we'd write it out on paper, right? This makes sense. Now, the problem is, if you put this into your calculator just like this, if you said 1.7 times 10 to the sixth, and then divided by 2.7 times 10 to the minus 11th. What your calculator would do is it would divide by 2.7 and then multiply by 10 to the negative 11th, because the calculator doesn't understand that the denominator has to stay together. Okay, so there's two ways to fix this. Okay, the first way is really lame and kind of inelegant and a pain to keep track of. You always need to put your denominator in parentheses. Okay, so you'd use these parentheses buttons here and here, and make sure your denominators are in parentheses. Now, that's a pain to keep track of, especially when you move on to more complicated problems where you've got lots of parentheses and things to keep track of, and it also makes your calculator harder to read. Okay, but this would get you the right answer, but it's not my favorite. All right, the other way to do it is to do it here. Now, if you use the second EE value here, this is what you do. You don't type in times or 10. So all of this times 10 gets replaced by an E. Okay, that's what this E means. This E means times 10. Okay, so you get 1.7 E6. That means 1.7 times 10 to the 6th. And then you're dividing it by 2.7 times 10 to the minus 11th. See how that works? And now, because of that E value, the calculator automatically knows, all of this stays together. Okay, and you don't even have to worry about putting in the parentheses. Without that in there, you'll get some bad answer. Okay, and it would really suck. Trust me, it really sucks. It does not feel good to be like, I set up my problem exactly perfectly and then fail at the calculator. All right, that's no good. All right, so anyway, do some practice problems. Make sure you understand how to do these using your calculator. Okay, I highly suggest using your own calculator. I will not allow you to share calculators on a quiz or an exam. Okay, and the calculators that I have are not that good. I mean, they do the math fine, but understanding how to use the calculator is 3/4 of the battle for some of these problems, because it's really easy to use somebody else's calculator and not know exactly how it works, and then you just miss the problem because you didn't know how to use the calculator, and that sucks. Anyway, so do your practice problems. Let me know if you have any questions.